Okay. This is a trust frame. Trust frame. We need to know how can we deal with a trust frame. There is an internal tie here, and here is a frame. How can I deal with this internal tie? Okay. What's the first step? Calculate the degree of indeterminacy. What's the degree of indeterminacy? How many redundants and how many equations? How many redundants do I have now? I have 2, 1, 2, 3, and you know that any tie has 1 redundant. So I have 4 unknowns here, minus 3 equations, so it's 1 statically indeterminate. So I have to remove 1 redundant for the next step, which is the main system. Okay? So I will remove the tie. When you find a tie, please remove it. It will be easier for you when you remove the tie. So the main system will be like this. Here was a tie, and I removed it. And the same loads like this. So this is the main system. Okay? What is the third step? Please draw bending moment for the main system, which is a statically determinate structure. Draw bending moment, which is called M node. In order to draw the bending moment, I have to first calculate the reactions. How many reactions here do I have? I have XA and YA. And XA will be to the left. I have only one horizontal load. So XA has to be equal to 1 ton, and to the left from the other side. And here there is YB. Okay. How will I deal with the distributed load here? Will I concentrate it 1 concentration or 2 concentrations? Or the question again, will I deal with the distributed load as a 1 distributed load from C to B, or 2 distributed loads from C to E, it's the first one, and then from E to B, the second one? What will be the right answer? If I dealt with this load as a 1 distributed load from C to B, that will be right for M node. But I know in case 1, I put unit load instead of the redundant I remove. And here is a tie, I remove the tie. How can I put a unit load instead of a tie? You know, a tie is like a truss member. It has 2 equal and opposite forces. So when I put the unit load instead of an internal tie, I will put 2 loads like this. Right? One at D and one at E. In this case, in case 1, the moment, which is M1, will be separated at point E here, right? So when I integrate M node with M1, I have to separate the M node at point E. So again, if you are answering the question for only case node, for only M node, okay, you can deal with the distributed load as a 1 distributed load BC. But you are using M node with integration with M1 that will be separated here at point E, divided at point E. So you have to, from the beginning, deal with the distributed load as 2 distributed loads. You can't concentrate it 1 time. You will take the mark of M node, okay? You will take the full mark from M node, but when you draw M1 and you are trying to do the integration between M node and M1, you will waste the time and here you will divide the parabola you already drew in the M node to two parabolas. So why wasting the time? So from the beginning, okay, divide it. So I have here two distributed loads, 2 times 4, 8, and 2 times 4, 8. Okay, let's calculate the reactions. Take moment at A. So 8 times 2, 8 times 6, and then 1 times 4 minus YB times 8. I think YB will be equal to 8.5. Sigma Y equals 0. I have 2 8s, which is 16. YB 8.5, so YA will be 7.5. Let's draw the moment. It is a frame. How can I draw a moment for a frame? I have first to calculate the moment at the joints. How many joints do I have? I have only one joint here. The moment will be 1 multiplied by 4, which is 4 in this direction. So the other direction has to be also 4 in the opposite direction. How many distributed loads? I have 2, as I said, CE and EB. And how I draw a bending moment diagram for any distributed load? I have to calculate the moment at the beginning and at the end, and then join and PL square over 8. So now I have to calculate the moment at E, because I am dealing with CE as a uniform distributed load. The beginning, okay, and the end of the load, so I have to calculate the moment at point E. So ME, let's calculate the moment from the right. It will be equal to 8.5 multiplied by 4, and minus 8 multiplied by 2, which will be equal to 2, I think. 2. 8.5 times 4 is no, 2. 8.5 times 4 is 36 minus 18. 34 minus 18. So 18, right? 32 and 4, 36 minus 18.
34 minus
36 minus
34.
All the calculations 34? This is 34 and this is 16. So this is 18. What's wrong? It's 18, right? In which direction 8.5 times 4 is the biggest moment, so it will rotate with the tail of the arrow below the tail. Okay, let's draw the bending moment diagram, which is M node here. M node. The column CA, the moment at A equals 0 and at C equals 4. For CB, it's divided to CE and EB. The moment at C is 4 below the datum. The moment at E is 18 below the datum. And the moment at B is 0. So join the 4 and the 18, and then PL square over 8. And the 18 and 0, and then PL square over 8. PL square over 8 will be equal to 2, 4 squared divided by 8, which is 4, and this is to be the same value 4. So this is M node. What will be the next step? Case 1 and draw M1. Case 1, draw one more time the main system. I'm drawing the main system one more time. And then put unit load instead of the redundant you remove. What did I remove here? What is the redundant? I removed the force in the tie BE. To put a unit load instead of a tie or a truss member is the same meaning. So we have to put two loads equal 1 ton in opposite direction. And here you are assuming that the force inside the tie is tension. You can assume a tension or compression. So in this direction or in the other direction. So I made this assumption. So I removed all the loads. I put only unit load instead of the redundant I removed. And then I have to draw bending moment which is called M1. But first I have to calculate the reactions. What are the reactions here? I have here YA and XA, and here I have YB. This is point E, and this is point D, and this is C. How can I calculate the reactions? I have a diagonal forces. They are not in the X and Y direction. So I have first to make a resolution for the 1 ton, the force which is 1 ton. In this direction and in that direction. Where is the angle? I have here, this is 4 and this is 3. So this is the angle theta. Sine theta is 3 over 5, which is 0.6. And cosine theta, 4 over 5, which is 0.8. Where is theta here? I think this is theta. So this is close to theta, will get a cosine. So this will be 0.8 and this will be 0.6. The same here. This will be 0.8 and this will be 0.6. And the one is not here. Again, what about the reactions? If you are taking sigma x equals 0, 0.8 and 0.8 in the opposite direction, so xa will be equals to 0, will be equal to 0, right? What about sigma moment at A? When you take sigma moment at A or at B, these forces will eliminate each other. These forces, if you are getting the 1 or after resolution the 0.8 and 0.6, all of them will eliminate each other. So the reactions here, all of them will be equal to 0. How can I draw the bending moment now? So I have only a 1 joint at C. I have to calculate the moment at, what is the moment here at C? It will be 0.8 multiplied by 3, which is 2.4. And the other direction will also be 2.4. What about the moment at E? 0. What about the moment at D? 0. So what will be the diagram of M1? It will look like this. Here, 2.4 and 0. And on the other side, 2.4 and in the middle, 0. So if I didn't divide M node, look what is the shape of the M1 here, what is the diagram of M1? It's divided at point E. So if this was one parabola and I didn't make 2 concentrations from the beginning, here will be one parabola from the 4 to 0, and here it's divided at point E, a triangle and nothing. So that's why from the beginning I divided the whole distributed load into two distributed loads. Okay? Now I can calculate delta 1 node. What is delta 1 node? It's the integration M1 with M node divided by EI dl. No, this is not the right rule. Delta 1 node is not the integration of M1 and with M node divided by EI dl. There is another term that we neglected when writing the formula of the integration of the delta 1 node. What is the other term that we neglected? It's plus sigma n1 n node divided by EA multiplied by L. What is this for? For frame. What is the second term for? Truss or tie. They have the same meaning. In the last example, there was only a frame. There wasn't any ties inside the frame. So the second term was neglected. That's why we neglected the second term in the last example. But here, when it comes with a frame with an internal tie, or we can call it a trussed frame, we have to go with the general formula for calculating the displacement. The general formula for calculating the displacement is not only the integration of the moments, it's also the summation of the normal forces of the tie or of the truss member. Okay? Let's go through the equation. Let's start with the integration of M1 with M node. Here, for the part EB, no moment in M1, so the part EB will be neglected. Take care, for the part CA, I was drawing a triangle, a whole triangle for the whole member CA. But here, it's only for CD. DA has no moment. So now I have to divide the whole triangle that was at CA. I have to divide it at point D. So here it will be equal to 1. So when integrating M1 with M node, for the first part C, D, it will be here a triangle with a trapezium. Right? And for the second part CE, here is a trapezium with a parabola, and here is a triangle. So the trapezium first with the triangle, and the parabola with the triangle. What about the second term? N1 and N node for who? For the frame? For the frame members? For CA and CB? The normal force in the frame member? No. The second term is only for any truss members or for any ties. So what does N node mean and what does N1 mean? N node, it will be related to case node. The main system is called case node. And this is called case 1. Right? So, the N node means the axial force or the normal force in the tie in case node. Were there any ties in case node? You already took the decision and you removed the tie in the main system. So N node will be equal to 0. What about N1? N1 is the normal force in the tie from case 1. Here is the tie. You put by yourself a unit load instead of the tie because you removed it. So what is the axial force in the tie in case node? It will be equal to 1. And it will be positive or negative depending on whether it's tension or compression. What about sigma? What does sigma mean? Sigma here means if there is a lot of ties, a lot of truss members, so you have to do this N1 multiplied by N node multiplied by L. L is the length of each truss member or the length of each tie. So you have to do this for every tie. But here I have only one tie, so I will not feel the sigma. I will not feel the word sigma, the summation, because I have only here one tie. And in addition, the N node equals to 0, so this whole term will be equal to 0. And it will remain again integration of M1, M node divided by dI, dL. What about delta 1, 1? Integration of M1 squared divided by dI, dL plus sigma N1 squared divided by EA multiplied by L. N1 squared. What about the integration of M1 squared first? Here's the M1 squared. Triangle with itself. Another triangle with itself. Sigma N1 squared will be equal to. So here N1 will be 1. So 1 squared multiplied by L. What is L? The length of the member, the length of the tie. This is 3 meters and 4 meters, so the length of the tie is 5. And here divided by EA. And what will be the condition? Delta 1 node plus X delta 1 1 equal 0. Here it's given that EI is 15,000 ton meter square and EA is 30,000 ton. So take care, it's not EI here and EI here, so you can remove EI from both sides because the right hand side equals to 0. No, take care now. Yes, delta 1 node is only EI because the second term was 0, but delta 1 1 has both of them, has EI and has EA. Okay? And from here you can calculate X, which is the force in the tie DE, and then you can draw the bending moment. Okay. Let's talk about the cases of symmetry. What about the first frame? I think it has here a line of symmetry or an axe of symmetry, right? What does that mean if I'm having a line of symmetry inside the frame? First, I have to check, I have to double check that it is symmetric. The symmetry is not only the loads, not only the dimensions, the symmetry for the factor of I as well. So this has to be like 2I, and this has to be the same factor, 2I. So not only the dimensions, not only the loads. This is the first case of symmetry, but I have also to double check that the member BE is not loaded. If the member BE is loaded, so this is not a case of symmetry. So the first case of symmetry, when I find a line of symmetry above a frame member. BE is a frame member. This case, again, the frame member, the column EB, it has to be unloaded. If it's loaded with any load, so no symmetry. In this case, you can draw only half the frame, like this. And you can remove the member BE. But what will I put instead? This is the question. Here is the distributed load, and here is the concentrated load. Six meters. What will be, or what will I put here instead at point E? So I remove the member EB. I will only draw half of the frame because the other half or the another half is symmetry or is symmetric to the left half. So the question is, what is the behavior of this point? What is the behavior of this point? As we talked before, if I am talking about a point in the 2D, how many displacements can a point have in the 2D? It can move horizontally, it can move vertically, and it can rotate. So it can have three displacements: horizontal displacement, vertical displacement, and rotation. What about the behavior of this point? Look at the original frame. Is this point allowed to move vertically? As we talked before, the beginning of the term, I think, I told you that any reaction eliminates the displacement. If I'm talking about point A, and A is fixed support that has X and Y and moment reactions, so the displacements here at point A, all of them are equal to 0. The horizontal displacement at A equals 0 because there is a horizontal reaction. The vertical displacement at A equals 0 because there is a vertical reaction. And the rotation at A equals 0 because there is a moment, a reaction of a moment. What about the behavior of a hinged support A? It only has a vertical reaction and a horizontal reaction. So the horizontal displacements is 0 because there is a horizontal reaction that eliminates the displacement in its direction. And the vertical displacement is also 0 because there is a vertical reaction. But the rotation is not 0 because there is not any reaction here that is a moment that eliminates the displacement in its direction. So the rotation here is not equal to 0. The same meaning here. My question again. The behavior of this point E. Is it allowed to move vertically? No, the answer is no. Why? Because here there is a vertical reaction at the fixed support that will eliminate the vertical displacement of this point. So the vertical displacement is 0. What about the horizontal displacement at E? Is there any support that has any reaction that eliminates the horizontal displacement at point E? No. If there is here any support like a hinged support or a fixed support, so it will eliminate all the horizontal displacement in all the plane DEF. But I don't have here any support that has a horizontal reaction. But the horizontal displacement is also equal to 0. Why? Why the horizontal displacement at E is also equal to 0 in this case? Because of the symmetry. Because of the symmetry. You are pushing horizontally from the left side the same loads that you are pushing from the right side. Because of the symmetry again. So you are pushing equally from both sides, so the point E will not move either right or left. If the loads were not symmetric, so point E will move in any direction. But here, because of the symmetry, so point E is not allowed to move horizontally. So no vertical displacement, no horizontal displacement. What about the rotation of point E? What about the rotation of point E? Because of the symmetry, point E is not allowed to rotate. Okay? So that means that point E is not allowed to rotate, not allowed to move horizontally, not allowed to move vertically. That means that I have to put a fixed support here. This is the definition of the fixed support. No horizontal displacement, no vertical displacement, no rotation. So when you find a line of symmetry above a frame member in a symmetric frame, you can draw only half of the frame. You can remove the frame member, the vertical frame member BE, and you will put at point E a fixed support. That is a rule. You don't have to think about it one more time about the displacement. I'm just explaining why did I put a fixed support here. What about this case? I think there is a line of symmetry here, right? This is the second case when the line of symmetry is above a hinge, an internal hinge. Again, you can only draw half of the frame like this. But what will you do at point E? What will we put here? Will it be free? Or will it be roller? Or will it be hinged support? Or will it be fixed support? I have to think. Okay? At the end, you will recognize it once you see in the exam. Line of symmetry above an internal hinge, so you know what will you put here. I'm just brainstorming with you why I put such what support or what the behavior of the point that will be at point E. Let's talk about the vertical displacement. Is anything avoiding point E to move vertically? Here, the vertical reaction at the fixed support avoided or didn't let the point E move vertically. Is there here anything that is avoiding the vertical movement of point E? No. So that means that the vertical displacement at point E is allowed. What about the horizontal displacement? Again, because of the symmetry, the horizontal displacement is equal to 0. What about the rotation? And take care, this is a hinge now. A hinge has two rotations. A rotation right and a rotation left. That's why in the determinate, the virtual determinant, there was one of the requirements, calculate. What did I ask you to calculate at the hinge? Relative rotation. That was one of the requirements. Relative rotation. Can I ask you to calculate a relative rotation at any point that is not a hinge? No, because at any point, the rotation right and the rotation left are equal. The only point that has a different rotation before it and after it is the hinge. That's why when I asked about the rotation at the hinge, I asked to calculate the relative rotation. It's in Arabic called Dawran Nisbi, okay? Relative rotation. So that means that there is a rotation right and a rotation left. So here, nothing is avoiding the rotation of the hinge E. So now I am thinking about a point that has a vertical displacement and a rotation, but the horizontal displacement is equal to 0. What is the properties that I am looking for? A roller support like this. The only reaction, the only displacement that is equal to 0, the horizontal displacement, right? So it has to only have a horizontal reaction. It has only to have a horizontal reaction. So if you put it like a regular roller support, it will be having only vertical reaction. If you put a hinged support, it will have both horizontal and vertical. But here, the only displacement that is equal to 0 is the horizontal displacement. So the only reaction here, it has to be a horizontal reaction. So that's why I thought about this kind of support, a roller support in a 90 degrees position. Okay? Again, you are not asked in the exam to prove it. Okay? When you see an axis of symmetry, line of symmetry above a vertical member, you have to eliminate this member and put a fixed support. When you see a line of symmetry above a hinge, again you can draw only half of the frame and put this kind of support. This is the third kind of symmetry. The axis of symmetry is neither on a frame member nor on a hinge. This kind of symmetry, you can't work on half the frame. You are not allowed, because when you think about the behavior of this point, you will not find any kind of support that will work with it. So in this kind, you have to work in the whole frame. You can't divide the frame into two halves. Okay? Let's talk about the yielding supports. We talked about the yielding supports in the superposition, and it will be the same in the virtual world. What was the effect of the yielding supports in superposition? It was having two effects. The first effect was on the main system, that I was not free to choose any main system. I have to remove the redundant that is in the direction of the support that yielded. The second effect was in the condition. Instead of the right hand side was equal to 0, no, the right hand side will be equal to the value of the displacement or the yielding that happened in the support. Let's talk here. I think this is similar to the last example. Frame was having two hinged supports. When I decided, or when I calculated first the degree, 2 and 2, 4, minus 3, so the degree is 1 here, 1 statically indeterminate. And when I decided to choose the main system, I asked you, what do you want to remove? Do you want to remove the horizontal displacement here, or horizontal reaction here, so the hinged support will turn into a roller? Or you want to remove the horizontal reaction here, so the hinged support at B return to roller? So we choose what to remove. But here, if he asked to draw the bending moment diagram and he told you, please draw the bending moment diagram due to the given loads in addition to a horizontal displacement at B, so you have to remove X3 and you have to choose the main system to look like this. You don't have the choice. And if he told you, please draw bending moment diagram due to the given load in addition to a horizontal displacement at A equals 1 centimeter, so you have to remove XA, and this has to be your main system. Okay? The same as in the superposition. What about the condition here? Instead of delta 1 node plus x, delta 1 equals 0? No, it's not equal to 0 now. It will be equal to the displacement that was 1 centimeter. So you will put 0.01 meter. Okay? What about the sign? We talked about the sign before. The rotation, the clockwise is positive, the anti-clockwise is negative. What about the horizontal displacement? Let's say if the horizontal displacement is to the right, so this will be our positive sign. If the horizontal displacement is to the left, this will be our negative sign. Okay? That's it.